Okay, I'm really pleased to welcome Professor Madhavi Krishnan to the final colloquium of the winter semester. Professor Krishnan did her undergraduate work at Anna University in Madras, India, and then got a PhD at the University of Michigan in Ann Arbor. And then she moved to Europe to do a postdoc supported by the Humboldt and Curie Fellowship at the Technical University of Dresden and ETH Zurich. And this time, I think I remember that really important contribution on the sort of electrostatic levitation in cavity. I remember that paper very well. It really impressed the community. And then there was a brief stint as a visiting scholar at Harvard. And then Professor Krishnan became professor at the University of Zurich from the Swiss National Science Foundation. And then moved to Oxford in 2018. Professor Krishnan has some prestigious prizes, such as the Nernst Haber-Bornstein Prize in Physical Chemistry for outstanding scientific achievements in physical chemistry, and the 2020 Corday Morgan Prize of the Royal Society of Chemistry for the invention of the sort of a colloid trap. And so without further ado, I'm really pleased to be able to hear your colloquium, and that's it for me.
Thank you so much, Walter, and thank you to Bill as well for the kind invitation to talk to the McGill physics community. I'm really sorry I'm not there in person, but maybe I'll get to fix that at some other point. So just to start off, I want to make good use of the time that I have. The fact that everyone's taken the time to show up at the end of a very long and hard academic term. I'm going to launch right into it and tell you ahead of time that the scope of the talk is going to be extremely narrow. It's going to be focused on electrostatics. So electrostatics in the fluid phase. And in the beginning, I'm going to show how understanding electrostatic interactions helps us use electrostatics as a tool to understand molecules, look at biomolecules and charged objects in a new light. And then I'm going to switch gears and show how electrostatics strikes back, as in, I'm going to show you all a very important aspect of it that we fundamentally don't understand, experiments where the phenomena are sort of upside down compared to what the theories tell us. So there's these two angles. In the beginning, we'll act like everything is normal and use what we know as a tool, and then we'll move on to more fundamental aspects, new frontiers that are opening up as a result of our being able to do very precise measurements. Okay. So hopefully this slide advance thing works. Yeah. Okay, so the beginning is all about trapping matter using thermodynamics. So if you look at the last 100 years of the way people have tried to manipulate objects of interest, from atoms to ions, it's always been the fundamental, the sort of abiding theme has been apply fields to your object. Now, most of these traps, for example, the optical trap, you will find that the strength of the interaction that you get has a polarizity term in it, which invariably scales, which is, it scales as the volume, which means that if you have something gets 10 times smaller, you lose by a factor of 1,000 in your ability to interact with it. So if you're interested in doing room temperature experiments like we are, not, cooling things down to 2 Kelvin and so on, which is fine in the gas phase, but if you're interested in biomolecules that have, thermal motion and structural deformation and so on, at room temperature because of thermal perturbations, then KT is an energy scale that you're competing with all the time, and KT is fairly large at 298 Kelvin. So when some stuff gets small, it gets very hard to interact with it when you have a fixed energy scale. So this problem, if you try to apply fields to stuff, you start losing that game when you're looking at nanometer-sized objects in fluid. That's my message. So something fundamentally different needs to be done. And so we said, okay, stop applying external fields. Why don't we look at thermodynamic interactions that are there for free? For example, what I mean is, for example, the electrostatic interaction at a charged surface. It's a long-range force that's there essentially for free without applying any external fields. You can think of other types of forces, dispersion forces, other electromagnetic forces. They're all in there, and molecules respond to them quite strongly. It's just like most of the time, experiments are done in the bulk, far away from surfaces and so on, where you could actually harness these forces because they're quite strong. So think of, your glass of water. The inside is negatively charged, and you have a potential that decays exponentially. That's well known. If you have a charged object, a light charged object, that object will experience a repulsive and exponentially increasing force of interaction and that follows naturally. The point is that I'm arguing that we've never used these kind of intrinsic interactions before, so maybe we should start trying to do so in a controlled fashion. So now, I talked about wanting to trap matter without applying external fields. Okay, so what if we had a parallel plate system? Well, the obvious thing would happen. The object would hang out in the middle. Now let's put a hole in one wall. What happens? So if our dimensions are all right, we can have a non-zero potential here where the walls are close together, a zero potential where we've created this divot, and then back again, it goes high outside. So left to right, you have a minimization of interaction energy, let's say, for a light charged object. And that's all that this trap really is. It's a thermodynamic trap by virtue of, that works by virtue of purely repulsive interaction with the surroundings. So when we first did the calculations, it seemed like, with very achievable dimensions, dimensions and structures, feature sizes that were very achievable in the laboratory, that we would get pretty large interaction strength. So half a kT per charge, which is a lot. If you think of the average molecule having, 5 or 10 charges, 5 to 10 kT in an exponential is a lot of time spent in that trap. So it seemed like it was going to work. And so the initial experiment was just, exactly like how you'd imagine it. Put some holes in one side of a parallel plate system. It's all glass or all silica, whatever. And then we threw in some gold particles. This particular imaging technique is, based on the scattering of light from gold particles. But we found that, individual gold particles would simply find a trap and sit there because that's the thermodynamic minimum. And these particles would just stay there essentially forever until the experiment got unstable. So this was getting a lot done by doing very little, as in no focused optical beams, no apparatus, nothing, just getting the intrinsic forces in the system to work for you. So there's a lot of good work you can do with colloids and simply looking at molecules for a long time and so on. But we wanted to quickly, move in the direction of, looking at biomolecules. So within the spherical cow approximation, a protein is nothing but can be treated as a colloidal particle, and so or can be thought of as a colloidal particle. So we didn't, sort of wait too long before we made that step to just throwing in protein molecules that are labeled and finding that they were confined and trappable and stayed for as long a time as some of our highly charged gold particles. And keep in mind that we've crossed an order of magnitude in size, and dielectric constant has fallen. Protein is essentially a low dielectric medium, unlike a metal, and the physics is still there because it just works by virtue of static charge on the object surface. And so we have, for the first time at the time, we had a trap that could where you could look at a single molecule for a very long period of time. So a little bit about the physics. In the early days, we used to think of it in terms of, a sort of a point object, a non-interacting, or sort of let's say a test object, simply scanning a pre-existing electrostatic landscape. And this picture works well enough, where you say the electrostatic energy simply minimizes when the object is in the trap. Negatively charged object. But in reality, there's no such thing as an isolated negative charge. An isolated negative charge will carry its cloud of counter ions around it, which are oppositely charged. So if anyone makes an argument that the negative object wants to hang out here, then there's an obvious counter argument. Oops, my pointer is acting weird. There's the obvious counter argument that the counter ions would want to go the other way. And so there's something wrong with that picture. And what's wrong with that picture is exemplified in this movie, which I hope I can get to play. Okay, so this is looking challenging to get to work. Just a second, sorry, I think my laser pointer is sort of messing things up. Okay. Okay, so you see that you have a very charged object traversing this landscape, messing up all the electrical potentials. It's not clear at all that the object should end up at the location that I've said it would. The answer comes from looking at the free energy, obviously, not just the electrostatic energy. And you go through the equations and you find, well, the reason that this trap works, although you can bottle it up into an electrostatic argument like I've shown up here, it's actually entropic. But this is long known in the whole colloid physics business, that two charged plates will repel in solution, not because of an electrostatic argument, but because the counter ions in the gap resist compression. They behave like an ideal gas. And so when the object is outside in the parallel plate part of the system, the counter ions are compressed against the walls. Basically, they have less entropy. And if the particle goes and sits in the region of the indentation, the counter ion entropy is maximized, and that's what really gives you the trap. So although we talk about it completely in electrostatic terms, the underlying physics is entropic. Okay, so that said, I can now move on to show you, the kinds of things that can be done with it. So we started with gold particles, we did lipid vesicles, disordered proteins, globular proteins, and then we're sort of bottoming out at the level of a fluorescent dye, which is a nanometer in size and a nanometer in charge. So this principle can be applied over 2 orders of magnitude in size and charge. And to be honest, we don't care too much about size, we care about charge, as I'm going to show you. Charge sits in the exponential of this response and enables a whole bunch of things to be done. So, so I think this is the ideal community for me to sort of throw this thing out there, and I'll come back at the end and address whether this trap is a violation of EARNSHAW'S theorem or not. So Earnshaw said a long time ago that you can't have a trap in a static field. And all we have here is a static field. So let's keep this question in the background and maybe come back to it at the end of it. Essentially, this is saying in 1 over r square fields, you can't have any stable spatial minima because of the way the divergence works. Okay, so what are we going to do with this technique? We decided we don't really want to trap objects for very long periods of time. We're happy with measuring very accurately this escape time and doing something with it. So this technique is called escape time electrometry. And what we have here is we're looking at escape times. We're looking at molecules falling into traps, staying there for a while, popping out, and that gives us a sort of a residence time distribution that we call escape time. And you can fit this very, very precisely, and you get a lot of events, and you can get very, very small uncertainties. And now the interesting thing is that this escape time depends exponentially on this quantity we're interested in, the well depth. This is, Kramer's expression or first order kinetics, however you want to think about it. And it's a very, very convenient situation to be in terms of measurement, because the quantity you're interested in, which is sitting in the exponential here, the free energy, the well depth, depends appears in the exponential. So the quantity you measure, the time scale, depends exponentially on the quantity you're really interested in. That means you can have tiny changes up here, which correspond to big changes in your experiment. So that immediately means we can measure the well depth with extremely high precision. And it just so happens that if you use that electrostatic lumping type of argument that I was talking about, where you can just write free energies in terms of an effective charge times a electrical potential of the midplane of the system. So you have one experimental parameter you need to characterize and fix. Once you do that, you're measuring a thing called the effective charge extremely precisely. Now, this is where I'm going to say the physical system or the physics turns into a technology, because the rest of it is I'm going to tell you, or the next third of the talk, I'm going to say what we do with these precise measurements of effective charge. I mean, in some sense, who cares? So you measure something extremely precisely, unless you can make sense of it, it's worth very little. So I'm going to show you a couple of examples and then push that concept a little harder. So we're looking at this disordered protein that in terms of its structural charge, so if you went along the backbone of the protein, if you were an atom or an atomic scale probe and you counted the actual ionized atoms that there were, you would end up with something like -46. But the measurement is pointing to something lower, and also it's also giving it with very high precision, which means we need to take, if we believe what we're doing, then we need to take this number very seriously. So this is the unique sort of point for me to say what charge is in the fluid phase. Why do we talk about an effective charge, which is different? In the gas phase, you never speak of effective charges, you just have the charge on the ion and that's it. But the liquid state is fundamentally different. So first of all, you have chemistry going on. It would be nice if that's all that there was, but there's more than that. So this is a phenomenon called charge regulation, and chemists will be familiar with the idea that whether a group is charged or not depends on the pK of the group, the pH of the system, so whether the protons like to stay on or off. If you have a highly dense distribution of charge, like you can have in a biomolecule, then you just have a correction, you pick up a correction factor for collective effects. You just have a surface potential that empties the expression. Now, you have, in addition to that, the nonlinear response of the electrolyte. which then means that counterions in the electrolyte will huddle close to your object, thereby sort of creating a dressed ion, a dressed object, which has a lower effective charge. So all of this comes together. There are some simple criterion to know whether you're in the renormalizing regime or not, but if you do the math, you have to do all of this together and then you can compute an effective charge. Now I'm a little concerned that my clock says that we're already at 27 minutes. I hope that's wrong. I hope it's counting from some other point. Okay, so I'm just going to go on. Walter, shout if, when I have 10 minutes left or something. Okay, so that's what goes on in terms of defining what an effective charge is. So that said, you would have already picked up this got to be some dependence on the arrangement of charge in the object. So this is a good example for me to illustrate that. So go back to this disordered protein result that we had. It was supposed to carry 46 negative charges. If you do a full Poisson-Boltzmann calculation, and we assumed a simple sort of uniformly charged linear rod, which is a fair assumption for a polyelectrolyte, then you do get something smaller, 37 charges, negative charges in this case, but it's still quite far off from this 31 value. So, scratching our head, wondering what was happening, we realized that, of course, this particular protein is not a uniformly charged object. In fact, if you look at the sequence, it carries most of its charge huddled together in one section of the molecule. The moment that information was keyed in, then the calculated effective charge started to match very much what the experiments were showing, suggesting that, classic situation of having a spectrum or, inverse scattering problem, whatever, you measure something and then you've got to have a model in order to be able to understand something about the object you're studying. So this is, it was a nice example of things checking out because the measurement was telling us, hang on, you have, this particular object you're looking at has some structure in it, has some, non-uniform charge density in it, and that's what you're picking up in the experiment. Okay, so we went ahead and measured, basically any biomolecule we could get our hands on at the time. So going from nucleic acids to disordered proteins to globular proteins. With these large globular proteins, we could even tell what the dielectric constant of the interior was. I mean, in the sense that we knew it was folded because the charge we measured, so all the measured values are on top and they have errors on them. The calculated values are below. So these were very early measurements and we got pretty decent agreement between measurement and calculation. And for the disordered proteins, we could even tell that the object must be folded because the measured charge was so much smaller than the nominal charge expected for the just the structural charge, that it must be that most of that was buried in a low dielectric interior, suggesting that the protein is globular. If you look at the at a sort of a counterexample, this disordered protein that exposes all of its charge, essentially all of its charge to water, then we got quite close agreement between the structural charge and the measured charge. So 100 charges was about 90 effective charges in practice, and that was very similar to the calculated value. So you could really tell with a little bit of information on your molecule, you could start, for example, knowing from the simple measurement whether it's a globular or a disordered protein. This is sort of an example I like to show quite often. This is you have a situation where you have two molecules, a blue molecule and a green molecule, and one of them is migrating much faster than the other. There's actually a fairly small difference in charge between them, but you clearly see that the blue molecule is spending more time in the trap, immediately, saying that it's the one with the larger charge, and you're looking at the difference between, fairly small difference between two strands of double-stranded DNA, about a 10% difference. And you can already see the difference in their escape times, the difference in their charge by eye. This is, just like under a second worth of movie. And normally in the lab, and you're looking at literally two molecules, normally you would need several, at least an hour to do a usual sort of a traditional separation type of experiment to know the difference. So this is the kind of high sensitivity to object charge that we're trying to leverage in molecular measurements. Of course, we can tell the difference between tiny amounts of charge, mutation in a protein that changes the charge from like a positive group that turns negative. We can detect small differences in DNA, all of that. Trying to do good spectra is the direction we're going in. I'm going to skip this in the interest of time. This was just to show that the trapping a single organic molecule is essentially saying we are looking at a single ion, because if ions were going to emit light, and I mean a single cation in the fluid phase, this is how it would behave, because the physical properties of a organic molecule and an ion are essentially very similar. So the other thing we want to do is to look at individual molecules. Now, rather than pool all the signals into one, sort of lump them all into one average histogram, you can actually look at individual molecules, watch them hop through the landscape. And if you were to collect sort of every 3 hops, ask for an average escape time, you would know the escape time to within 60% because of the shot noise uncertainty. Now, 60% is usually large in a measurement. 60% uncertainty is not a great measurement, but we can leverage the fact that we have this logarithm in the picture. So the effective charge depends logarithmically on the escape time, which means even the errors are snuffed out. So 60% error on escape time would be less than 10% error in charge. So you could actually watch slow processes that change the charge of your molecule. For example, if it folded, or if it, some chemistry happening, then you would actually be able to see that in real time. And one direction we're going in is now to actually look at individual molecules and measure the charge of each individual molecule with high precision. So this is not ensemble measurements with high precision, but actually trying to get out, really highly resolved charge spectra, because this could be very useful in many sort of bioanalytic problems. So then coming to my sort of pet problem, which is shape, detecting molecular shape using electrometry, meaning conformation. Now, people know in biology, they know that of course, DNA has this electrical potential variation along the molecular backbone, and proteins are known to sense that, in the near field and so on. This is all very well known. But there is an angle that I think is less well appreciated, and this is shape matters at a larger distance as well, not just at the level of atomic contact where chemistry starts to become relevant and sort of chemical kind of thinking is very well established. So we wanted to establish this idea, and therefore we took advantage of this field of DNA origami, where they're now able to make all kinds of fancy structures and then changing the shape in a fairly controlled fashion. So this experiment, we received support from my collaborator Andrew Turberfield, who's an expert in DNA origami, and they made for us various shapes of DNA nanostructure carrying effectively identical amounts of structural charge, where we could probe just the effect of shape alone. So if you ask yourself, so what do these objects look like in practice in an experiment? What's the electrical potential distribution like? Then, although they carry identical amounts of structural charge, you see that the potential distribution around these objects is extremely different. And the effective charge picks up this. It's very, very dependent on the shape of the object. So you can already see where that's coming from. I used to explain this in terms of, in physics, you have a line charge and you have a point charge, and they have different sort of the potential around them decays differently, and you have pretty much the same thing in the electrolyte phase. It turns out that the electrolyte is actually more sensitive than the vacuum phase for subtle reasons. So when you say shape matters in the far field in electrolyte, it's actually even more true in an electrolyte than in vacuum, because in the gas phase, in the far field, everything looks like a point charge. Now, it turns out in electrolyte, even in the far field, you have the dipole, monopole, and all the multipole terms still showing up. I wasn't aware of this, so it's quite a nice coincidence that it turns out to be, able to sort of emphasize this concept in electrolyte phase. Okay, so what happens when you make measurements on these objects? So here's another table that I'm sort of gotten quite used to making for various things. And again, you have the same way of looking at it, which is the measurements are on top, the calculated values are at the bottom. Again, you find very good agreement. And you see that a tetrahedral sort of arrangement of charge, which is effectively like a sphere under our measurement conditions, this can have, although the structural charge is exactly the same, the effective charge can be almost a factor of 2 smaller than in magnitude than a line charge. Okay, so there's a lot of interest in understanding conformation in biology. And so we think that we have a nice sensitive tool that gives us a fairly cheap measurements and ability to discriminate conformation. Turns out you can also coarse grain this kind of view of things and just, sort of make mock-up spheroids that have the same geometric sort of properties as each of these origami molecules. And that's more than enough to catch the experimental behavior. So a tetrahedron behaves like a sphere, and a cylindrical long DNA molecule behaves like a prolate spheroid. Again, this kind of the way the free energy behaves as a function of shape has been looked at in the vacuum phase for conductors, various shaped conductors and so on, in a completely different and long-standing sphere of activity. And I think we're recapturing many of these, essentially the same concepts in the fluid phase. And then, of course, you can now, in the next 10 minutes, before I switch gears completely, I'm going to sort of close this thing out by saying we're moving in the direction of doing a bit of sort of structural biology with this technique, and I'll give you a few examples. So this is an example of a square tile, which is the structure that collaborators made for us, where you have 4 cylindrical bits of DNA next to each other in a horizontal arrangement, ostensibly. And here we have measurements that come out quite different from the calculation. So, and we start to wonder, should we take this seriously? So this is a value based on an X-ray scattering structure, and that's our value from electrometry. There's a fair discrepancy, about 10%. And so we said, okay, can we start doing structural modeling to see what we need to do to capture the experimental measurement? So the calculation, the original calculation was based on a known X-ray scattering structure. Now we want to say, well, what do we need to do to tweak our structure to capture the measurement? And all it turns out is we just need to change the spacing between the 4 cylinders. And if we're about less than an angstrom larger than the X-ray scattering structure, we capture our result. So I don't think it's too much of a stretch to say that because we're measuring under no salt conditions compared to X-ray scattering experiments, our helices are just slightly more spaced apart than in the X-ray scattering experiment. So here is, this is us making baby steps in the direction of getting some coarse-grained structural information by doing high precision electrometry experiments, which keep in mind, it's just watching molecules under a microscope, room temperature, nothing fancy. So where we want to go with this problem, it may be slightly ambitious, but then we have to try, this is the RNA structure problem, where there aren't techniques to do this, and people use AI when they want to know these days. If you want to know the structure of whatever RNA sequence, you rather do AI than anything else, because there's very little, structural techniques are just hard to apply to secondary structure in RNA. So that is something I think where our technique, it's not going to give you atomic structural information, but it can certainly give you some type of a validating view. Is the structure that your AI predicted really what we see in experiment or not? So I hope that that's a sort of a dialogue that electrometry, or dimension that electrometry can sort of bring to the structural biology problem. Now, in the interest of time, I should probably skip through this bit where we tried to go beyond a little, push our structural abilities a little beyond, massive changes in conformation, and really measure the rise per base pair and the diameter of the double helix. So I'm going to rapidly skip through details here and just go through the result, which is after a lot of hard work and extremely precise measurements. So it turned out we needed measurements with 0.1% precision, which meant getting 10 to the 4th, 10 to the 5th escape events, and so on. So I'll skip all of the description of the way we got here, and show that electrometry can actually measure the rise per base pair. So bDNA and aRNA are slightly different structures. bDNA is longer and skinnier, aRNA is shorter and fatter, but for the same exact structural charge, we could measure the rise per base pair of these double helices with sub-angstrom precision. In this case, it was 100 picometer precision. And the radius of the DNA, of the double helix, we could measure with about angstrom precision. And when we change the size of the cation, we would also see within, because we're using a continuum dielectric point ion picture, this kind of description is actually sensitive to where the ions sit. So if I were to sort of scoot back to a picture like this, so our understanding of DNA is basically that you can model it as a charged cylinder. You have this continuum outside that has a uniform dielectric constant smooth ion density, but that picture has to break down at an interface where the graininess of matter becomes evident. So our question was, are we going to see this line where the continuum starts, are we going to be able to pick up an effective ion size, in other words? So we're in the unique position that we can do precise measurements and we can change the size of the ion. So are we going to be able to pick that up? And for some reason, I was very chuffed about that. And we managed to see something in the end where we found that the radius of the helix is actually sensitive to the radius of the cation. Notice that I have lithium, the tiniest cation, at the high end of the radius, but that's because, in terms of hydration in the solution phase, lithium turns out to be the largest hydrated ion. So to me, that was quite a nice result, because for the first time, I think in the molecular context, this sort of a picture emerges, which is, we see where the ions sit. And there's even a hint, if you push this, if you really push the interpretation to the limit, you might even claim that we see a little bit of the hydration share. While we know of this picture implicitly, or the colloid people and interface science people would have seen this picture for the interface, the stern layer and all of that. This is known for surfaces, but there's not much experimental data directly probing it. I definitely think that, knowing this for a molecular interface, I don't think the experimental techniques that really yield this picture in this direct fashion. And so I think this is very satisfying in some sense that electrometry can deliver that kind of structural information on the molecular interface as well. So I think I have about 10 minutes left to pull the brakes on this and shift gears. First, we'll answer the question of whether the trap is a violation of EARNSHAW'S theorem or not. And after that, I'll show you where all this marvelous electrostatics that we claim works within the scope of the Poisson-Boltzmann equation and all that. I'll try to show you that can be, not really very true under certain conditions. And I'll try to show why. So, okay, so is the trap a violation of EARNSHAW'S theorem? No, is the short answer. So we have a different kind of a Poisson equation. So the mathematical answer to this question is, well, of course, you look at this equation and clearly see that when you're in the charge cloud, this side, the right-hand side can be manifestly non-zero, which means that you can have local minimum. As long as you're within the Debye cloud, you can have a local minimum. EARNSHAW'S statement that you can't have a trap in a static field was a system with no constraints. All he said was there can be no accumulation of charge or magnets or masses at any point in space. But the moment you apply a constraint, which is, let's say you take this bunch of charges in your system and say they have to sit on a line, that's the simplest sort of constraint you can think of. Then you find that you can very well have local minima. So in our system, we have maximization of entropy is the and minimization of free energy are major constraints on the system. So I think we're out of the remit of EARNSHAW'S theorem, and therefore happily do not have to worry about any violations of having a trap in a static field. Okay, so with that, I'm sort of concluding this entire trap business and what we can do with it in electrometry and molecules. And I'm going to look at this, my proposition of bringing electrostatics to light from a different point of view, which is I'm going to now talk about all the violations of our standing equations and bringing perhaps introducing corrections to them or bringing additional physics into the picture that actually explains the experiment. So the context of this bit of the discussion is a long-standing problem which some people will be aware of. It's called the like charge attraction problem. Like charges are not supposed to attract according to gas phase intuition, we expect them to repel. But in the 90s, there was this field that got quite hot. Lots of experiments were done showing that particles, like charged particles, were attracting. Now I've just put some images here to show you what they mean. Colloidal experiments sense repulsive spheres would expect to simply do a random arrangement, not show any particular interactions with each other. But some experiments were showing interactions where under some conditions you could have cluster formation. I'll show you some of these experiments now. And at the end of that wave is when I was sort of monkeying around with these confined systems and throwing in charged objects into charged confinement and finding some pretty weird things where we found DNA would spontaneously stretch out at the corner of a nanoslit. And things were happening that when again negatively charged objects were behaving in a funny way. in a way like they were experiencing some type of a long-range attraction to another negative object. It's not just DNA in our experiments, colloidal spheres would also hug the walls of a slit rather than hang out in the middle or be far away from a charged wall. We would find opposite behavior, charged objects would go. So this was, us coming in from a different angle, colliding on a collision course with this very important and big problem in the colloid field, which I was not particularly interested in at the time. So one set of experiments, which I will use as a sort of flagship to say why the whole field died down and then why it needs to revive now, were concerned experiments. This is Seth Fraden's data where they looked at polystyrene spheres and they constructed these radial probability density distributions and extracted pair potentials. Now, a purely repulsive pair potential, you would expect to, I'm sorry, I'm just going to sort of draw a phantom line like that. You expect an exponentially increasing repulsive interaction energy, but they were finding minima, and minima at extremely long distances, so about 10 Debye lengths, where everything's supposed to have died out. The Debye length is of the length scale on which an interaction will decay to 1/e. So 10 Debye lengths, really nothing should be happening. Of course, in the meantime, I have developed a reason, which I will get into, that explains why we could have these counterintuitive attractions between like-charged particles that are supposed to repel by all counts, especially at long range. But the problem at the time was in the whole like-charge attraction field is that they were measuring extremely weak energies. Now, 1/10 of a kT is a tiny energy. And when theorists who got into this area and started doing theory and finding, many people proposed various explanations, but then the whole thing got debunked when somebody came along and said, this is all imaging artifact. It was proving quite difficult to gain traction theoretically. And then I think once people cast aspersions on these experiments saying that they were just imaging artifacts, if you analyze your data differently, this weak sort of attraction would go away, then this whole field died down. But if something is true, if there's a true phenomenon, it will keep coming back regardless of these what happens with sort of the ups and downs of the way a field develops. So more recently, Jay Groves in Berkeley has shown experiments where these are again colloidal microspheres. Now these are our experiments following up on those experiments by Jay Groves. Now you're looking at negatively charged silica particles. You can see hopefully that there's some kind of motion. These are not stuck, or these are not, they're not irreversible aggregates or something. There's slow reorganization. You can see the inner particle distance is massive because the particle diameter is 5 microns. So these particles are hanging out at roughly a micron worth of spacing between them, which is 5 to 10 Debye lengths. And you're viewing something sort of in real time, in the sense that if you're seeing the interaction, then this is not an artifact. And I'll show you that these interaction energies are quite large, and it's time we started taking this seriously. So you can do careful experiments, change the salt concentration, and as you increase the salt concentration, the clusters go away. So there's some clear dependence there. And if you look at the radial probability density functions, again, you find massive cluster structure at low salt concentrations goes away as you add salt. And if you do some simulations and extract what the underlying pair potential must be to create these structures, then you find you're talking, 5 to 10 kT, which is not something we can sweep under the carpet any longer. Okay, so then, so these are explained by this new explanation of ours, where the first term is the exponential repulsion that we all know from conventional electrostatics, and the second term, when B is less than 0, is an exponentially growing attractive energy. And when all these constants are in the right balance, in the right relationship to each other, then you end up getting a minimum. So these are systems that should be eminently well described by our standing theory, Poisson-Boltzmann theory, which is similar to DLVO theory and all of this. So the standing theories that explain colloidal interactions or particles in electrolytes should catch these interactions under these conditions. There are some exceptions to these theories, but not under these conditions, not under low concentration of monovalent ions, not with low charge densities. So there's something serious going on. It gets even more weird because if you do the experiment with positive particles, you can't get clusters with positive particles. So so this is, again, you don't see any cluster structure. If you model the interaction potential, Positive particles give you this monotonic exponential, the promised DLBO, Poisson-Boltzmann exponential repulsion as expected. Again, so Jay has pointed this out in this paper some time ago, saying that these interactions are asymmetric, but we don't know what to do. Because by no means can you have, why on earth? So we have the same Maxwell's equations in a fluid phase. This system cannot break charge reversal symmetry, right? So the force is symmetric because there's a Q square, it's a symmetry. So if you change sign, the force still remains repulsive. In a fluid, we just have a slightly different Poisson equation. The force, the corresponding force is exactly the same thing with this effective charge that I've been ranting about. But it's basically the same thing. And even in a fluid, we definitely expect charge reversal symmetry. Okay, so I have about 5 minutes left to get my point across. And like I said, this problem is actually quite a long, long-standing and long-lived problem, because although it cooked to the top in the 90s, it's been known since the 40s. And this is Rosalind Franklin crystallizing viruses and seeing that these viruses form clusters, and they have these ordered arrays, and they're separated by large distances. They seem to be held together by long-range forces because they shouldn't be forming this crystalline formation. And they seem to be weak, attractive, and repulsive forces. Now, repulsive would be okay because they're all like charged, and most viruses will have quite negatively charged. I don't know what their particular viruses were in terms of charge, but they're already saying they seem to be weak, attractive forces operating through the water. So, of course, we always say, if you're a physical chemist, anything, or even in any other field dealing with water, whenever there's something weird that people don't understand, it's always blame it on the water. So we can do that. But I hope to be able to tell you in exactly what way. So what exactly is water doing here, in our view, that gives you A, an attraction between like charged particles, and B, only if they're negatively charged, not if they're positive. So there is some symmetry breaking, and you can see already from the structure of the water molecule, it's not symmetric. Or it has some asymmetries in it. I'm going to say that it's these asymmetries that are going to propagate forward and break the symmetry in the interaction between charged particles. Now, the electrostatic part of the interaction is exactly like the textbooks. Nothing wrong with that per se. But in the total interaction that you observe in experiment, there's an additional massive contribution that can mitigate and reverse the sign of the canonical repulsion. So how exactly does this work? I find this very elegant, and I think it's simple to grasp. So I'm going to try and get it across in a few minutes, but I apologize if it doesn't come across easily. Well, the picture is like this. If you have a positively charged ball, then water orients with its dipole pointing, as I've shown, with its negative oxygen atoms towards the positive ball. If you have a negative surface, then water points the other way. The dipole is flipped. Now, the big question, what happens at an uncharged surface? So this can be, for example, think of a pure air-water interface where everybody knows there's electric potential interface and so on. And that's what I'm driving at. So it turns out at an uncharged surface, you might suppose that water simply rotates isotropically, nothing happens. Or you might think, well, there's a symmetry breaking there, so maybe water does, and these are cartoons, this is sort of an exaggeration of the effect. Water doesn't point that strongly towards the bulk, but there's a tendency for it to point ever so slightly its hydrogen atoms towards the bulk, simply because the bulk is more polarizable and supports more hydrogen bonds. So that said, this gives rise to an offset electrical potential. So at zero charge, you will pick up a slight negative electrical potential with respect to the bulk at zero charge. And then as you charge up the surfaces, the potential, of course, changes accordingly. It gets more positive if the surface is more negative if the surface is positively charged, and the other way. But it's this offset that is a key symmetry breaking feature. Were water to orient completely isotropically, then you would get no intercept. That line would pass through the middle, and we wouldn't be observing the symmetry breaking in experiments, in my view. So when you integrate that potential as a function of charge, you get an interfacial free energy. Again, it's a very simple quantity. All we need is that potential from molecular simulations. Integrating that gives you this non-monotonic behavior on one side, monotonic on the other. If you didn't have this, you would have a symmetric relationship and nothing funny would be happening. Just forget the stuff on the side. This just tells you that all that we're accounting for, all we're saying is that water has a slight energy bias to point one way rather than the other. And it's very simply explained. So what happens for why this affects an interaction in the fluid phase is as follows. If you have two objects that are charged in the fluid phase and they come close together, then their groups will charge regulate by that mechanism that I first pointed out, that the charge regulation, the dependence of charge on pH and pKa and so on. So in order to minimize their free energy, two objects will reduce the magnitude of their charge. When negative objects do that, the interfacial free energy due to water contributes a reduction. So water would counteract the electrostatic repulsion that we know from our standard picture of two interacting charged objects. If you look on the positive side, then when two positive objects approach, they reduce in their charge. What does the water do? The water contribution, interfacial contribution of free energy goes up. So this is a symmetry breaking of an interaction that has one sign, that has the same sign essentially as the particle charge. So an attraction, a reduction in free energy if you have negative particles, and positive repulsion if you have negative particles. So I think this is a minimum model that catches, that explains symmetry breaking in the experiment. And again, we're not proposing anything very new because people have seen this forever. Simulations have seen this, know that water flips around. Interfacial spectroscopy has seen this. So at high pH in silica, water is this way, and the other way when you have low pH, which is basically neutral surface. That may not have been very obvious, but it's been picked up in experiment. All that we're doing is calculating what's the thermodynamic contribution of this behavior, because it's not present in continuum models. Continuum models will see water as just plastic. It's sort of a dielectric continuum with no molecular features. The moment you introduce this molecular picture and account for the behavior of molecules, this just it emerges naturally. So I'm not going to bore you with the equations. All I'm saying is that you just need to include this, the interfacial free energy term, and you get this flipping of the sign of this force. And the important thing is that it's of a magnitude that's substantial enough to cause havoc in experiments. So with that, I'm going to conclude this bit. And I'm going to say, previously we had this electrostatics picture, and it works remarkably as long as you're not in this part of the parameter space where water starts to interact or starts to change in orientation strongly. The moment you add this water behavior, then you have this additional term, which can be of the same magnitude but opposite in sign. In fact, it can even be larger than the electrostatic propulsion, which means it's huge. And this essentially explains the fact that you can get attractions between negative particles, repulsions between positive particles. And I don't have time to show you that this phenomenon is not unique to water. If you change the solvent, where, to a situation where the solvent behaves in the opposite way, then we can show that positive particles attract and negatives repel. So I think there's a huge component in solution phase of electrostatics that hasn't been visible. And this whole thing has actually come to the fore because we were able to do very precise measurements with well-known molecular probes of, we're able to probe electrostatics in a very precise way. The experiments are more compelling with colloidal particles, but they actually came out of doing electrometry very carefully. So with that, I'm going to sort of end kind of on time. Thank you very much for, coming to the talk and listening. And I'm quite happy that we started with gold nanoparticles about a decade ago and are now managing to look at structural biology questions, interface science. And, these are the kids, the people in my lab who've done all the work that whose data I've shown to do. And we're looking for bright and motivated postdocs. So if you know of anyone who would be interested or are interested yourself, then do not hesitate to get in touch. I think with that, I'm happy to take any questions. And I apologize. I think there's been one person in the chat who's, okay, so sorry, that was a comment by Walter, so that's okay. Yeah, so I'm happy to take questions.
So people have questions? I can just say them orally.
Yeah.
Oh, Paul has a question. So can you unmute and ask Paul?
Yep. Yeah, great talk. Very lot of interesting stuff in there. Question in terms of the electrostatic trap, in terms of capability, because just thinking of things one could explore with it. So when you, is it possible to trap the proteins and things and then change pH conditions and stuff, or does that mess around in terms of the isoelectric and the charges so that your escape times change significantly?
That's a fantastic point, Paul. Now, the thing is, all that is possible. The only problem is we're working with this nasty material called silica, which I absolutely detest. The thing is, you have material that's highly acidic. So supposing you could make you could coat all your surfaces with a nice and acidic polymer like polystyrene sulfonate, which a lot of people do. Then the walls will remain effectively at constant charge while your molecule would change, and you could see all the dynamics. I mean, you could see, you could effectively pH change. But right now we're stuck with this material and we make slow progress when it comes to changing, surface chemistry. But if we could just nail that surface chemistry issue, we could do all of this.
Yeah, that would be fantastic. We can chat later in terms of the analysis stuff we discussed, and I'll let Walter continue. But fantastic talk.
Thank you.
Any other questions from the audience? Text? I don't think so.
I have a question.
Yeah.
Okay. Hi, Madhavi. Great talk. I'm sort of a fan because I'm doing work with Walter, and I've had to read some of your papers already, so fan. What I was going to ask is, for example, how important is, for example, the characteristics of the fluid dynamics of the system when taking these sorts of measurements? Because that's something I always think about is, for instance, at that level, at that scale, so really small particles, maybe some perturbations on the fluid, for as minimal as they can be, might, I don't know, change the dynamics a little bit of the molecules or something like that. Like, how does that actually happen? Yeah.
That's an interesting point, because so you're talking about, for example, a flow field. What happens to the dynamics in a flow field, right? Because in an ideal experiment, there's purely diffusive. That's the way we think about it, and so on. So we actually do a lot of experiments with an imposed flow. And it turns out, so naively one would think, oh, well, the flow is going to drag the particle out, right? Because there will be a drag force, and it's like a particle in a tilted potential, washboard potential. Actually, it turns out that the electrostatics is those wells are quite deep, and the force, if you calculate the energy, the drag force, the energy corresponding to a drag force, these particles are so tiny that there's not much of an effect. There's some effect, but not much. Not as much as you would think, or not to the extent that you could use flow as a sort of parameter to modulate. So yeah, we generally don't worry about flow. We actually use it sometimes to get a lot of statistics.
All right. Thank you. Thank you so much.
It's a good question, though.
Okay. I have a question. Also, it's fantastic. It's amazing that you can pick up these really fine-scale details, like these like angstrom changes in bonds in these measurements. Amazing. Anyway, my question concerns this work with the DNA nanotechnology. You had this interesting array of shapes you've been exploring, and I was thinking that if you have some anisotropic shape, the actual far field potential should be anisotropic, right, around the object.
Yeah.
But you've been looking at averages for that potential in the measurements. Is that?
Yeah, we are looking at averages. You're absolutely right. So in our picture, and it may need correction and it might change the numbers slightly, our picture is the model that we relate the measurements to. Let me put it this way. The model that we relate the measurements to is a conformation where the object is at the, of course, we take into account positional fluctuations, rotational fluctuations, but ultimately, we're looking at an orientation. There will be a dominant, a Boltzmann-weighted orientation. For example, a rod, like the rod-shaped model, is not going to stand vertically in the slit. It will be sort of parallel in the slit. Right? So you're absolutely right. We are sensing some particular conformation or some were dominated by a particular orientation and a particular position location, although there would be fluctuations around that, we are dominated by.
I see. Do you think that the escape rates might be anisotropic? Like if I have something oriented in a certain chamber, right? Maybe the escape, if you have to one side, is different from the escape 90 degrees to a chamber 90 degrees away or something, right?
You're talking about whether there needs to be a specific orientation at the point of escape.
If the shape is oriented in a certain way and the potential is different, it's anisotropic, it might be if the escape, say to the left, is different from escape, to 90 degrees to that direction, maybe, for example.
Yeah, I mean, I definitely think that there will be the coupling of, orientation toward with
Right.
What the minimum local free energy is in terms of, you could, right now our traps are all isotropic.
I see.
So if you made them isotropic, yes, you could probably play with this.
Might be interesting. The other thing I had, this interesting, this idea about the effect of water on surfaces. I had always had the understanding, and it's somewhat vague in my recollection, that the effects, the attraction of negative to negative was due to like charge fluctuations, like a kind of van der Waals effect due to charge fluctuations. And I was curious if that's like a competing explanation or if it's part of the story or what you're.
So the thing is, Walter, you're right in the sense that when you introduce divalent cations into the system, then the Poisson-Boltzmann picture breaks down and you actually have this kind of what is called the van der Waals type of effect, a charge-induced dipole interactions and the system become attractive. So all of that, those exceptions are well known in where the moment you have, so those are the breakdown points of the Poisson-Boltzmann picture, where charged correlations become important, divalent cations or low dielectric media. Both of those enhance electrostatic interactions strongly, and the main field picture breaks down. Yes, you can have attractions, but nobody has been able to come up with any kind of explanation for attraction in this textbook Poisson-Boltzmann regime. And yet you see massive attractions and they are at an extremely long range. So that's the other thing that's very hard to explain. How do you get 5 to 10 kT worth of attraction at, when the electrostatics is supposed to have died out completely? I'll tell you why. The reason is even when the electrostatics has died out completely, the tail end of the electrostatic potential is seen by the water molecules. There's a tiny effect per water molecule, but you have a zillion water molecules. When that's integrated, it can give you something substantial. That's all. I mean, that's why this picture, I think, it catches a number of features, which I think is why it really, the answer was never going to be found, in my view, within the framework of electrostatics. It was something from the outside, because look at the charge, the symmetry breaking. It's never going to be there in a charge symmetric electrostatic picture. I mean, that is if you buy the symmetry breaking in the first place. So
interesting. There's another question. I know that Andrew has his hand raised. I didn't know that. So, and
oh, yes. Sorry if you're finished. So this was a really interesting presentation. I know very little about these traps, fluidic traps and things, but I saw there was one animation you showed where you were sort of tracking an individual molecule following its path through this trap. And I was just wondering, how do you know that it's the same molecule? I saw other animations with lots of molecules coming in and out, and I'm just wondering, how do you know it's the same individual molecule?
Oh, okay, so I had a calculation animation, which was really me animating the object traversing the landscape, if that's the one you mean. But that's just sort of an illustrative thing. The others were real movies. So where you saw a lot of flashes of molecules, the sort of, the green flashes on the blue background. So mostly those were real movies of actual experiments. And if the question is, how do you know you have one molecule? That's a great question. First of all, we know roughly the intensity of a single molecule. So when there's two of them, you immediately see a blip that's much brighter. And you will see, quite often, you can see them sort of do dynamics, and then one of them will leave because it's a repulsive situation, so one will exit. So it's quite easy to see when you have more than one occupancy. We typically do these experiments with quite dilute conditions so that you have the average occupancy is less than one molecule per trap. But yes, that's a very good question. It would upset the whole picture if you sort of piled in a bunch of molecules into the same trap. You wouldn't be able to do these experiments. You wouldn't have clean experiments anymore, or clean measurements. I don't know if that answers the question, which is a very good one.
I see. No, I think it does. Thank you very much.
Great. So I think no more questions for the audience, I think. Great. Well, let's great talk and thought, I think. I don't know how we do this on Zoom.
Fine, I
raise
can,
your hands,
I'll
right?
just, I'll sort of, yeah, that's, yeah, I see the,
Your hands, right?
right. So thank you very much.
Yeah, excellent.
Yeah.